In previous goals, we talked about galvanic cells or voltaic cells, and these are a thermodynamically favorable process, so you don't have to put anything into it. It just happens. It happens because of the activity series of metals that we observe. This next goal, we are going to be talking about those that are not thermodynamically favored. And so in order for these to run, you have to add electricity or a battery of some sort to run it. So a good example of this would be splitting water, like electrolysis, or an electrolytic cell where it's running backwards from the activity series, and electroplating. An electrolytic cell, this is a voltaic cell that does not occur without outside help, and that is because what should be oxidized we're actually reducing, and what should be reduced we're actually oxidizing. And so a battery or a current, so plugging something into the wall, makes this happen. So this battery or the current, it acts as an electron pump. And it will pull the electrons from the anode to the cathode. So your anode and your cathode, the definitions still remain the same. So your electrons always flow from your anode to the cathode, and it goes in alphabetical order, A to C, anode to cathode, or you could even do oxidation to reduction. That's still alphabetical order. So electrons are pulled from the anode and pushed to the cathode by this power supply. And again, it always goes anode to cathode. So in this first picture, I have a normal thermodynamically favored process. I don't have to put in any outside energy. I can go from that iron to the copper. But if I wanted to go backwards, I would have to put in to a battery. Let's look at electroplating. So it's for protection, and it can also be for beauty. So in this example, we are electroplating a spoon. So we're making a silver spoon. So it would be a silver plated spoon. And notice there's a battery there that's driving the reaction. We just have one electrode, and then the spoon acts as another electrode. So that silver bar is acting as the anode, and then the spoon that we are electroplating, that is the cathode. As far as the process goes, we have a silver solution there, and as those electrons come over into the spoon, then it will be plated with the silver from the solution. Electroplating, we can actually measure how fast it takes to electroplate something, or how much current it will take, or how much metal can be laid down on our spoon over a certain period of time. And there is a formula, and it looks like this. It's a little bit confusing because that Q is supposed to measure the charge or the coulombs, and then the T is the time, and the I is the current. The current always flows opposite from the direction that the electrons are flowing. So if the electrons are flowing left to right, the current would be flowing from right to left. It's a little bit weird concept. But instead of this, what's on your data sheet, I think it's easier to memorize this. So it's seconds times amps equals coulombs. And here's a little silly sentence. It's sexy amps are cool. We do use Faraday's constant, and this acts as the bridge from moles of electrons to moles of the metal or grams of the metal that's used. So some other things that you'll see with electrolysis or electroplating, coulombs is a C, amp is the current, and a lot of times it's they say amps, so that's why sexy amps are cool, I think is more helpful. Here's that equation one more time here. You can rearrange it. And then, of course, here's Faraday's constant that helps us get from the charge to the moles of electrons. In this problem, we have a current of 0.452 amps is passed through an electrolytic cell containing molten sodium chloride, and it's done for 1.5 hours. What is the mass of products formed? And we do have our oxidation and reduction half steps there. So our products formed would be this chlorine, the chlorine gas, and then this sodium, and it looks like it's a liquid sodium. So our strategy is to calculate the total charge of the electrons transferred, and then to use Faraday's constant to convert to moles. I'm going to use that formula, sexy amps are cool. So seconds times amps equals my coulombs. It says 1.5 hours, so I just need to convert that to seconds so I can put it into my formula. So very quickly sketch out that conversion, and I get 5,400 seconds. So let's go ahead and put that into our formula right here. And our coulombs is 2,440 coulombs. So now I'm going to take that and I'm going to use Faraday's constant to help me get how many moles of electrons I have and then how many moles of each of these products. So let's first of all start out with our chlorine, and then I'm going to look at the stoichiometry. For every 2 moles of electrons, I get 1 mole of that chlorine, and then this just becomes a stoichiometry problem. And I get 0.90 grams of my chlorine. And we're going to repeat the process now for the sodium. So this time in our equation, we have 1 mole of electrons for every 1 mole of our product. So it's a little bit different than the chlorine in that regard. And for my answer, I get 0.58 grams of the sodium. How long does it take to electroplate 5 grams of zinc from aqueous zinc ion solution with a current of 50 amps? So I'm going to use that formula, sexy amps are cool. And to find coulombs, I need to find the moles of the electrons. And then once I do that, then I can plug it into this formula. So let's start off with our 5 grams that are given to us. And I see for every 1 mole zinc, I have 2 moles of electrons. All my units will cancel. And I'm going to be left with coulombs. And I have 14,757. No sig figs there. So we can probably round that to about 15. Let's carry an extra digit. So let's do 14,800 coulombs. So then I'm going to put this into my formula. Sexy amps are cool. And I'm going to solve for the seconds. So I'm going to divide each side by the amps. So I'll put this coulombs on top and I get 296 seconds. So with electroplating, how many electrons are required is important. So a metal with fewer electrons would plate faster. So if I had silver, which only has 1 electron needed in that equation, and this is with the current that's given, so the 50 amps, a metal with more electrons would take longer. So more electrons would have to come across in order to plate that. What is the quantity of electricity in coulombs necessary to deposit 50 grams of silver from a silver nitrate solution? And there's our formula there, so I know that 1 electron is involved. So I'm going to start with my 50 grams and divide by the molar mass of silver. And there's 1 mole of electrons for every 1 mole of silver. And then multiply it by Faraday's constant. All your units should cancel. And I get 14,700 coulombs. So that's how much is necessary to deposit that 50 grams of silver. Metals react with oxygen and water and they are oxidized, and this is also known as corrosion. Some products of corrosion are actually protective, while others can really erode away that metal. The copper on the Statue of Liberty is covered with a thin layer of copper oxide, and this is an ionic compound, or it's also called a ceramic. And this actually protects the copper from corroding in New York Harbor. And so with the oxidation of that metal, we get something that's harder. And this doesn't penetrate all the way through the metal of the statue, only the very top few atom layers. Aluminum, like an aluminum foil, behaves the same way. When you actually pull out a sheet of aluminum, you're really looking at aluminum oxide. And that's because aluminum is very reactive and it will react with the oxygen around it. To look at pure aluminum atoms, you would, if you ripped the piece of aluminum foil, that ripped edge, there would be some raw aluminum atoms there. And again, it's very protective. It doesn't extend all the way through the sample, just that top few atom layers is where you will find this coating. That's why aluminum foil still bends like a metal, because it's just the very, very top atom layers that will be this ceramic. Well, what about iron? So iron oxide is rust. And if you look at rust, it's really, really powdery. And so not all ceramics are the same. It's still an ionic compound, but its properties are very, very weak. And so when this happens to our metal, like this car door, we see that it just takes away and chips away at the metal. And so this is very, very destructive. So what can we do to protect metals from this corrosion? We know that some metals are okay, like copper and aluminum, and they won't have this detrimental corrosion, but things like iron, we need to be able to protect them, to protect those things that we've made. With corrosion, you usually need oxygen and water. And here is just the reaction of iron forming rust. To prevent the corrosion, here are some strategies. We can paint the surface. We can galvanize the surface, which means we use chemistry and electricity to put a thin layer of zinc on something. That's what galvanization means. And it's just done through that electroplating that we were talking about. They put the metals they want to galvanize into a big vat of zinc salts, and then they run a current through it, and then that will cause the zinc to stick to that metal that they've put into the solution. Can also use a sacrificial anode, and you often might see these sacrificial anodes stuck to ships, or maybe you have a family boat that you have a zinc sacrificial anode. The idea of this is this sacrificial anode will provide electrons to the iron, and so the iron won't corrode, the anode will. This also works in your water heater. So in your water heater, there's a piece of zinc, and that is in your water heater, and it will constantly, because it's in contact with the steel of your water heater, it will provide electrons for the steel, and so the steel won't rust. This sacrificial anode will again corrode or oxidize. So this is what your water heater sacrificial anode looks like when it needs to be replaced. Here's just another picture showing that if you have an iron tank under the water, it's going to be exposed to both water and oxygen. And so they will attach a piece of magnesium onto it that will provide electrons for the iron. So the magnesium will corrode and not the iron.